All right, welcome calculus. This is section 3.2, the power rule. Whenever you need to, pause the video and copy things down, but this is a rule that it makes derivatives a lot easier if they're polynomial functions, making derivatives easier since sometime in the 17th century. So here we have a really long polynomial, and if I wanted to take the derivative of it, it would take me a while because there's a lot going on here. When I have to do like the f of x plus h minus f of x over h as h goes to 0, I did it on the side, and it took me a while to get it, and the answer is down here. If I have to take each of these terms and replace the x with x plus h, this red box here is me just doing the f of x plus h part. This becomes x plus h to the fifth, x plus h to the fourth, x plus h to the third, to the second, and so on. X plus h to the fifth, I made Pascal's triangle to expand that in yellow. X plus h to the fourth, I expanded that in green. To the third in blue, to the second in purple, to the first in orange, and then the 8. And then I distributed the 3 in, so this becomes negative 3x to the fourth, negative 12x to the third, h, negative 18. You can kind of see that right here. This 5 gets distributed in down here, and then this 2 gets distributed in down here, and then the 11, and then we're there. So that's just the f of x plus h part. Then we have to subtract f of x, which is this. So what I did here is I wrote the f of x plus h part right here minus f of x. So f of x is down here. So when I subtract f of x, I'm going to have a minus x to the fifth, a positive 3x to the fourth, a minus 5x cubed, a minus 2x squared, a plus 11x, and a minus 8, which cancels out with this x to the fifth, this 3x to the fourth, this 5x cubed, and so on. All the remaining terms are going to have an h in them. All the ones that didn't get canceled out, all of them have an h. If I factor out those h's, this is what's left over, and these h's are going to divide out, and so the remaining expression is this. There's no fraction anymore. And as h goes to 0, now that the h's divide out, I can plug in 0, so this h becomes 0, this term becomes 0, this becomes 0, and every term with an h in it becomes 0. The remaining terms are the 5x to the fourth, the minus 12x cubed, the 15x to the second, the 4x, and a minus 11. So that's how we can find the derivative. And there's a shorter way of doing it, and that's what the power rule is going to be. So in general, if I have some function of the form x to some power, think power rule, then the derivative of that function is whatever that power is times x, and then we subtract 1 from the power. Okay? So in the example above, or the example that we, in this big example up here, if my power is, say, like x to the fifth, the derivative, so if y equals x to the n, and the derivative is n x to the n minus 1, that 5 just comes down here, times x, and then the power is 5, so I gotta do 5 minus 1, which ends up being 4. So the derivative of x to the fifth is 5x to the fourth, and you can see that right here. The derivative of the first part of the derivative is 5x to the fourth. So it's a very easy way of doing polynomial functions. Kind of a pseudo proof of like how that happens is just kind of like looking at the original one that we were doing. When you expand everything out, all the terms that don't have an h get canceled out with the f minus f of x part. Every term that's left does have an h. So when you factor all the h's out, the only term that only has one factor of h is this first term here. Everything else is going to have h to the second, h to the third, h to the fourth, h to the fifth, h to the sixth, all the way down. So when I take out all the h's, they're all going to have an h still in them except this one. So this is the only term that's not going to have an h in it. So that's the only term that kind of survives when we plug in 0 for h. And so that's going to be true with all of the terms that survive. All right, so pseudo proof. Oh, by the way, this is the power rule. So given, say I have a function that's x to the n, I want to prove to you that its derivative is n times x to the n minus 1. So the derivative based on the limit definition, because that's how I'm going to have to prove it, is this. And if my function is x to the n, then it becomes x plus h to the n minus x to the n over h. So when you expand x plus h to the n, I'm just going to make this triangle again. And so this x plus h to the n part, the first term is going to have x to the n. Then your next term is you're gonna subtract 1 from that power, but then you have an h. Then your next term you're gonna subtract another 1 from that power, but then h gets to the second power. And you kind of go on this pattern where it goes h squared, h cubed, h all the way to h to the n. And then this exponent's gonna go down from n to n minus 1 to minus 2 to minus 3, all the way until we get to the last two terms. The last two terms is gonna have an x in it. The second to last term is gonna have an x in it, and an h to the n minus 1, and then the last term there's going to be no x in it, and you have h to the n. So this is like x plus h to the fifth. The first term would be x to the fifth, the last term would be h to the fifth. Now Pascal's triangle tells you what the coefficients are, so all of these things are going to have a number in front of them. The number is not going to matter except this one right here. And the second term number is always going to be whatever the exponent was. So when the exponent is 4, it's the coefficient for the second term is 4. When n equals 3, the coefficient for the third term would be 3. If we're looking for the nth term, then the coefficient for that term is going to be n. So the second term and the second to last term are both going to have that. It doesn't matter what the other ones are. I'll show you why in a second. So this is x plus h to the n, and then I have this minus x to the n all over h. Now, just like I said, this x to the n and this x to the n are going to cancel out. And then every term left is going to have an h in there. They're going to have a couple factors of h. So once I factor out that h, I'm going to have this n x to the n minus 1, and that h is factored out. And then I have this term here, but I took one of those h's out, so now it's just h to the first. And then I'm going to get a bunch of other terms, but all of them are going to have an h. This one's going to next one's going to have an h squared, then an h cubed, then an h to the fourth, all the way until I get to this last term, which is if I take one h out of that, I'm just going to have one less factor of h. The h's divide out, just like they always do. And then now with what's left, I can plug in h equals 0. There's no h here, so I get n x to the n minus 1. But this is going to become 0 because I'm plugging in 0. And all the terms in the middle are going to have 0, are going to have h's in them, so they're all going to become 0, including the last one. So then you truly do get x times n, x to the n minus 1, n times x to the n minus 1, sorry. So there's your pseudo proof of in the general case, why does the power function's derivative is that. Okay. Quick other rules. If there's a constant in front of a function that you're differentiating, you can just take the derivative and multiply by that constant. So if I said, I have x to the third, times, let's say, 4, and I want the derivative of that, well, it's going to be 4 times whatever the derivative of x to the third is, and using the power rule, it's going to be 3x to the second, so that ends up just being 12x squared. So when you have a constant outside, it just gets multiplied in. And if you're taking the derivative of a sum of functions, you can just take each derivative separately. So if I like x cubed plus x to the fifth, the derivative of x squared is just going to be the 2x because I'm using the power rule. The 2 comes down. 2 minus 1 is 1. X to the fifth, the derivative of that's going to be 5x to the fourth. Again, the power comes down, and we just subtract 1 from the exponent. So pause the video, copy these examples down real quick. All right. So there's my function. the derivative of that function, again, if I have the function x to the n, then the derivative is going to be n times x to the n minus 1. So if n is 2, it's going to be 2x to the 2 minus 1, which is just 2x. Here, if I want the derivative, it's going to be, let's see, I have 5x to the third. So it's going to be 3 times 5x to the 3 minus 1, which is 2, which is just becomes 15x squared. This is a constant function. The derivative of a constant function is always going to be 0. And here, I have 2x to the second. So this exponent, I'm going to multiply this 2 by this 2. So we get 4x to the 1, or just 4x. The derivative of 4x, you can think of this as 4x to the 1. 1 times 4 is 4. X to the 1 minus 1. And 1 minus 1 is 0. And 1 is a constant. The derivative constant is just 0. And x to the 0 is also 1. So this just becomes 4x plus 4 times 1, or 4x plus 4. Okay. I'm going to pause the video because my computer's about to die, and then I'll get the other half to you guys soon.